We now take a look at how to graph Philip the polynomial, part 3. We've already found out where the polynomial increases and decreases, and we found out where the polynomial is concave up and concave down. Remember that our polynomial was f of x is equal to x to the fourth minus 4x cubed plus 4x squared. What I've done here is I've taken our critical points, those of the function, which are 0, 1, and 2, and those of our first derivative, where our second derivative is equal to 0, 1 minus root 3 over 3, and 1 plus root 3 over 3, and combined everything together on one sign test. What this allows us to do is to consider the different shapes that we might see with a function based on the first and second derivatives. If both the first and second derivatives are positive, we get a concave up increasing shape. If our first derivative is negative and our second derivative is positive, then we get a concave up decreasing shape. If f prime is positive and f double prime is negative, we get concave down increasing. And if both f prime and f double prime are negative, then we get concave down and decreasing. So what I did was, based on the results from the sign test, I came up with the basic shape for each of these intervals. It's also going to be helpful to know what the roots of the function are. So I took the original and factored out x squared, leaving us with x squared minus 4x plus 4, which we then can factor to x minus 2 squared. So therefore our roots are x is equal to 0 and x is equal to 2. Both have an even multiplicity, which means they're going to balance off the axis in whichever way they go. F of 0 is equal to 0, f of 1 is equal to 1, and f of 2 is equal to 0. I chose those because those are critical points for the function, and it would be helpful to know what the y values are that correspond to them. So let's take a look at how this all gets put together. First, let's address the idea of what it means to be a relative maximum. There are two ways that you can prove that something is a relative maximum. You can show that f prime goes from positive to negative, which it does at x is equal to 1. If you look back at our sign test, f prime went from positive to negative. In addition, you could prove that we have a relative maximum at x is equal to 1 by showing that f prime of 1 is equal to 0, or is undefined, and f double prime of 1 is less than 0. If you look back at our sign test, you see that at either side of 1, we have a negative second derivative, so that fulfills what we need there. Relative minimums we get by showing that f prime goes from negative to positive. So that's way number 1. That's what's called the first derivative test. So as you see at x is equal to 0, the derivative went from negative to positive. And at x is equal to 2, the derivative went from negative to positive. You can also see we have relative minimums if we actually draw the little pieces as well. Notice also at x is equal to 0 that the derivative at 0 is equal to 0, and at x is equal to 2, the derivative at 2 is equal to 0. And in both cases, the second derivative is positive. So by the second derivative test, since f prime of 0 and f prime of 2 are both equal to 0, and f double prime at x is equal to 2 and at x is equal to 0 is positive, by the second derivative test we would have a relative minimum. Putting this all together, we have a little piece that decreases and is concave up all the way up to x is equal to 0. You can see that piece there. All the way up until the inflection point of 1 minus root 3 over 3, we have a concave up but increasing piece. Thereafter, up until we get to x is equal to 1, we have concave down and increasing. Then we have concave down decreasing until 1 plus root 3 over 3, a minimum at 2 comma 0, and you can see on both sides the function goes to positive infinity. Notice that at x is equal to 0 and at x is equal to 2, we have roots that bounce off the x-axis. So this is a way to put together all the features of our wonderful graph.